So moving from geographic coordinates to Cartesian coordinates, we call that a map projection. So why do we use these map projections in the first place? I would say there's two main reasons. First of all would be aesthetics. We can just use these to design attractive looking maps. The second one is that flat maps have historically been very important, whether that's a flat piece of paper or a flat computer screen. And since people want these flat maps, we want to try to minimize the distortion that they're seeing on that map. The types of distortions we can see in a map projection might have to do with the relative size of various continents, for example, or the shape of what's being projected. There can also be distortions in distance from one point to another on a map, or even the direction in which you think you're traveling if you're drawing a straight line on the map. So map design, let's start with that. There's a lot of beautiful maps that have been designed with map projections in mind. This is one example, a sort of heart-shaped projection, which is projecting the entire world and actually does a good job at some things like minimizing the distortion of area near the North Pole. We can see that the North Pole is not at the very top of this map. It's further down but in the middle of this map, and because all of the lines of longitude are coming back together there, it helps to minimize the distortion. Here's another example of a map projection that's specifically concerned with the design of the map. This is Buckminster Fuller. He was very much into geodesic domes and a lot of other things, but he designed this map projection. It's called the Dymaxion Map Projection, and sometimes it's called Spaceship Earth because it's designed to show the interconnectivity of all of the lands and the people that live on the surface of the Earth. What he's done in order to do this is he started with a globe, and then he's broken the globe into a series of flat triangles, and then expanded that so that all of the land is on one of those triangles, and the places where the cuts are to create this flat map tend to be in the ocean. So that we see he starts with the globe, flattens it out, and then flattens out the entire structure in order to make this map projection. The other reason, though, that we use map projections is to try to decrease the distortion. So as soon as we have a curved surface and we try to put it on a flat plane or a flat tabletop, there's going to be some distortion associated with it. One way that we can minimize the distortion in certain areas is to think about how we want to flatten things out. In this example here, we're trying to make a map of the United States on the curved Earth by putting it onto a flat plane, and this flat plane actually passes through a circle which is labeled as the standard circle or the line of true scale. Along that line of true scale, there would be absolutely no distortion because that's where the plane is actually touching the globe or the surface of the Earth, of the curved Earth. However, as we move towards the center of the map from there, what we can see is that whole ellipsoid surface on the left-hand side that is above that map surface is going to have to get squished in order to get filled into that area there. And that's where the distortion takes place. On the other hand, outside of the circle, the Earth is also curving away from that plane. So all of that is going to have to be stretched out in order to lay flat on that plane as well. So in both those ways, we're distorting this map in every location except for that standard circle, that undashed line on the right-hand side map, and the dashed lines are just showing where more and more distortion takes place as we move towards the center of the circle or away from the circle. One way to visualize distortion is by these things called Tissot indicatrixes. What this shows on the right is that circles are drawn on a map projection, and in this case, this is the plate carré map projection, and each one of those is a perfect circle on the right. However, if we were to project those back onto a globe, what we would see is that those would still be perfect circles along the equator in the center of that globe. However, as we move towards the North Pole and the South Pole, we can see that those circles are getting compressed into ovals or ellipses with their primary axis, their longer axis, oriented north-south. This is because the map on the right has stretched out those areas because it's trying to represent all lines of latitude by lines that are equally long. And that's just not the case. As we can see on the left, those lines of latitude are getting shorter and shorter. So these circles on a map are just a way, and on a globe, are just a way of showing where the distortion is occurring as we move from the map to the globe or the globe to the map. And sometimes we just use these to illustrate distortion. Because map projections are distorted, this would be an example of where a pathway seems distorted, even though it's the shortest path between Seattle and France. And what we can see is it does not look like a straight line on this map because of the distortion associated with this map projection. If we were looking straight down on this line on a globe, it would look like a straight line, and we could verify this by putting a piece of string between those 2 points on a globe, and it would be as taut or as tight as possible. But in this map projection, it appears as a curved line because of the types of distortions we get associated with some map projections. In this example here, we see Greenland in a lot of different map projections, and we can see that in all of these there's some distortion associated with them. Probably the least amount of distortion is with the one in the upper left-hand corner in part A, because it's more of a global type view. But even though we're viewing the globe, it's on a flat surface, so there would be some distortion associated with it. In the upper right, we see things are just stretched out as we go further and further to the north. And the one below that, D, in the lower right-hand corner, we can see here that one of the ways we've tried to compensate for this distortion is by using curved lines of latitude and having all of our lines of longitude converging as we move towards the North Pole.